Welcome to the sixth lecture in general topology. The topics that we'll explore in this lecture include dense subsets, nowhere dense subsets, and separable spaces. Okay, so before we start new material, we'll look at one of the exercises from the previous lecture. So let tau sub e be the union of the entire set X together with the set containing the entire set X together with all subsets of the set X such that the point P is not in the subset. Then this is the excluded point topology on the set X with P the excluded point. Notice that for every point X that is distinct from the point P in the space X, the singleton containing that point is open but not closed. And so the space is not T1 since it is not true that every singleton set is closed. Now, alternatively, using the definition, we can note that the only open neighborhood of the point P is the entire space X, and so it is not possible to separate the point P from any other point in the space. So as the space is not T1, it is also not T2 or Hausdorff. And so now we look at whether or not the space satisfies the condition for a T0 or Kolmogorov space. So for every point X that is distinct from the point P in the space, the singleton containing that point is an open neighborhood of the point X such that the point P is not in this neighborhood. Further, for every pair of distinct points X and Y, both of which are distinct from the point P in the space X, the singleton containing the point X is an open neighborhood of the point X, and the singleton containing the point Y is an open neighborhood of the point Y such that the point X is not in the neighborhood of Y and the point Y is not in the neighborhood of X. And so for every distinct pair of points, there exists an open neighborhood for at least one of those points not containing the other. And hence the space is T0 or Kolmogorov. And so the strongest separation condition satisfied by a space with the excluded point topology is the T0 or Kolmogorov condition. Okay, so now we're ready for a new definition. Let the set X together with some topology tau be a topological space. A proper subset D of the space X is called dense, or is said to be dense. Or everywhere dense. in the space X if and only if the closure of the set is the entire set X. So let's look at some examples. So let tau sub I be the set containing the empty set and the entire set X. Then this is the indiscrete or trivial topology on the set X. And let the set A be a non-empty proper subset of the space X. So we look at the empty set, the non-empty proper subset, and the entire set. In any topological space, the empty set and the entire set are both open and closed, and so they are their own interior and closure. In the discrete topological space, any non-empty proper subset is neither open nor closed. The only open set contained in the set A is the empty set, and the only closed set containing the set A is the entire set. And so the closure of any non-empty proper subset in a indiscrete topological space is the entire set X. And so every non-empty proper subset A of X is dense in the space X. So next, let the set X be countable. Let tau sub D be the power set of X, that is the discrete topology on the set X. And let the set A be a non-empty proper subset of the space X. Again, we look at the empty set, the non-empty proper subset, and the entire set. Now, in a discrete topological space, every set is both open and closed, and so each set is its own interior and its own closure. And so there does not exist a proper subset A of the space X such that the closure of that set is the entire space, and hence there are no dense subsets in a discrete topological space. So let tau sub P be the union of the set which contains the empty set together with all subsets of the set X such that the point P is in that subset. Then this is the particular point topology on the set X with P the particular point. And let the sets U and C be non-empty proper subsets of the space X such that the set U and the complement of the set C are in the topology. That is, the set U is open while the set C is closed. Now, every non-empty proper subset in the space with a particular point topology is either open or closed, but not both. The empty set is its own interior and its own closure. The open set U is its own interior. Now, every non-empty open set must contain the point P, and so the only closed set which contains the set U is the entire set. The set C is its own closure. Again, every open set, every non-empty open set must contain the point P, and so the only open set contained in the set C is the empty set, and the entire set is its own interior and its own closure. So every non-empty open proper subset U of X is dense in the space X with the particular point topology, since its closure is the entire set. So let tau sub E be the set which contains the entire set in a union with all subsets of the set X such that the point P is not in that subset. Then once again, this is the excluded point topology on the set X with P the excluded point. And let the sets U and C be non-empty proper subsets of the space X such that set U and the complement of the set C are in this topology. And once again, the set U is open while the set C is closed. Now, just as in a space with the particular point topology, in a space with the excluded point topology, any non-empty proper subset is either open or closed, but not both. Once again, the interior and closure of the empty set is the empty set, as it is both open and closed. The interior of the open set U is the set U. Now, the closed set containing the set U is the union of the set U with the singleton containing the point P. The set C is its own closure, and the interior of this set is the complement of the singleton containing P in the set C, and the set X is its own interior and its own closure. So notice that the only non-empty proper subset for which the closure is equal to the entire set is the complement of the singleton containing the point P. So the only dense subset of this space is, once again, the subset which is the complement of the singleton containing the point P, since its closure is the union of this set with the singleton containing the point P and is therefore the entire set X. Okay, so next we will prove a theorem that will give us some insight into what it means for a set to be dense in a given space. So let the set X together with some topology tau be a topological space. A proper subset D of the space X is dense in the space X if and only if every non-empty open subset U of X intersects the set D. So proof. Suppose that the proper subset D is dense in the space X, then the closure of the set D is the entire space. And so for every point X in the entire space, that point is in the closure of the set D. And hence, for every point in the space and for every open neighborhood U of X, the intersection of that neighborhood with the set D is not empty. That is, every non-empty open subset U of X intersects the set D. So conversely, suppose that every non-empty open subset U of X intersects the set D. Then, for every point in the space, every open neighborhood U of X, which is a non-empty open subset, the intersection of that neighborhood with the set D is not empty. And so every point in the space is in the closure of the set D, and hence the closure of the set D is the entire space, and thus the set D is dense in the space X. So notice that this theorem states that if a proper subset D of the space X is dense in the space, then every non-empty open subset U of X contains at least one point of the set D. That is, every non-empty member of the topology contains at least one point of the set D.